Hello and welcome to BoneUP, the podcast all about bones, how we make them, why we break them, and if we fully understand them. I'm David Armstrong.
Hi, and I'm Richie Abel. And over this series, we're going to be exploring osteoporosis, bones, what we know and what we're yet to discover. And we hope you will join us on the journey.
So, for anyone keen to learn more about our infrastructure of calcified collagen, this is BoneUp. Welcome to the fourth and final installment of our BoneUp Live recording at the ECTS conference in Innsbruck in Austria. We hope you enjoy the recordings.
Listeners, we're really happy to bring our next guest to you, Dr. Xenia Goldberg, who's a postdoctoral researcher in the Department of Clinical Research at the University of Southern Denmark. Welcome.
Thank you. Thanks for having me here.
Thank you for making the time. It's getting late in the day and everyone's a bit tired, so it's great that, we're still here talking about bones.
So we met a little while ago at the Danish Bone Workshop in Southern Denmark.
Yes.
And it was an absolutely fabulous conference, wonderful venue, people were amazing, it was such a welcoming atmosphere, and I was absolutely blown away by the research at the conference. It was absolutely amazing. So we've managed to pick up a few people at that conference for interviews. One of the things that I kind of came across for the first time at the conference was something called spatial transcriptomics, which seems to be a really big and emerging technique in bone science at the minute. Would you be able to tell our listeners a little bit about it?
Absolutely. So this spatial transcriptomics is about knowing more than we already know. Like it's never enough. We want to do more. We want to do it also even more fancy. So for many years it has been possible to actually take some tissue, you can mesh it, and then you can extract whatever component you'd like. You could have the mRNA, you could have the proteins, you could take cytokines from the serum. But when we do all of this, we would kind of mesh the tissue, so we would lose all of their structural orientation. We wouldn't see who the cells was sitting next to. We wouldn't see how the cells were located compared to each other. So we would be able to split all of these different cell populations without actually knowing where they were located. So it's always been a multi-step process to first doing this meshed bunch of things all together, and then trying some histology where we stain for 1, 2, 3 factors and say, oh, we see this factor in these cells, they are sitting right here, but we would never really know whether all of the genes we see, all of the proteins we see are in that exact same cell, or whether we have parts of the cells that are different or that are clustering at some place, especially within the cancer. It's very interesting to see what's actually sitting next to the cancer cells, because we have all of this tissue that's surrounding the cancer cells, and we're talking a lot about that these cells are actually helping the cancer, or at least parts of them are, and we don't really know which ones these are. And if we identify a signaling molecule, maybe it's not even important if the signal can't travel all the way to the recipient cell.
There's a tendency to sort of destroy the tissue as you're examining it up until now, so you're not quite sure where it all sat before you took it apart.
Exactly.
So tell us what you've been doing then.
Well, we have just, in my department at the molecular bone histology team, we have just, we were so lucky that we got a nice funding to buy some of this fancy new equipment. And when I did my PhD, I think we're almost 5 years ago now, we heard about this spatial transcriptomics. It was new, it was fancy, and it's very hard to do. So we've kind of been following it. And now all of the companies come in and you can buy a machine that's actually doing much of the work. So we got 2 of these machines and we've been testing them and making them run. One of the challenges in bone is that bone is hard to work with because it falls off these glasses we have. So there's a lot of optimizing. We can see nice results from spleen and brain and all these other fields of research, but the bone has been hard to get. But now the results are actually started to come. People manage to do it right now.
So what kind of experiments are people doing using the spatial transcriptomics with bone?
So there's a lot of things about this fracture healing. So trying to track what's happening after a fracture and which cells are coming in and which signals are appearing. That's what we see pretty much. We also see bone metastases from the cancer research because people get their biopsy taken, because otherwise bone research is kind of limited in where we can get the bones from. Often you don't give a bone sampled for research because it hurts a bit, and if you're just healthy, not everyone is willing to do that. But in these diseases where you have a bone biopsy taken as part of the diagnosis, that's also where we have things available. Otherwise, it would be mice studies with the fractures or also with cancers.
And we've already heard a couple of times this conference, how sometimes mice data and human data doesn't quite match up. One of the other things that really blew me away at the Danish Bone Workshop was bone reversal cells. Until that point, I hadn't heard anything about it, and I feel this is like an enormous discovery. Could you tell us a little bit about that?
Absolutely. So reversal cells were kind of what I've been working on throughout my whole PhD. We have during the bone remodeling is a process where old or damaged bone gets renewed. So every 10th year we say that our skeleton has been completely renewed, because when we walk, when we run, we'll constantly obtain these microfractures. And to avoid that our skeleton becomes bad because of these small fractures, we have to remove them. So we actually have a natural process happening in our body where old bone is renewed and new will be formed. So actually, patients would often say bone resorption or bone degradation, that's a bad thing. But in the case of bone remodeling, it's not, because we actually just remove something that's no longer sufficient and replace it with something new. And in a healthy person, this will be totally balanced. So you remove something and then you replace with the exact same amount. And earlier it has been we have the osteoclasts, they come in, they remove the bone, and then magically we have the osteoblasts coming in afterwards and forming the bone. But when the histologists started looking at the bone samples, it appeared that bone resorption is quite short, and it actually takes a while until these bone-forming osteoblast comes in. So there must be some kind of an intermediate step, and they started looking into what's happening in between. They saw that after the osteoclasts have been removing the bone, they're kind of sloppy. They remove parts of the bone, but they are not leaving a nice surface. So these cells are sitting around the osteoclast, and they are kind of preparing the bone surface. That's what we believe now, at least.
These are the reversal cells.
The reversal cells.
So that the missing link, they're a type of cell that comes in after the osteoclast is gone, before the osteoblast arrives. They sort of come in at night time and tidy the place up, ready for the osteoblast.
Yes,
that's
and
right.
When they were noticed in the beginning, people thought they were actually just young osteoclasts, not able to resorb bone yet. So, because they took up some of the proteins that's actually associated with osteoclasts. But later it was realized that they do not produce this protein themselves, so they are not osteoclasts. They are actually young osteoblasts, so they are the young bone-forming cells that are not yet ready to form the bone.
And even though they're bone-forming cells, you were saying they actually remove debris or remove bone tissue, so they're masquerading as osteoclasts, are they? Or are they're able to do both? Presumably they can remove bone tissue and then later in their life they can build bone tissue.
Yes, it seems like that, because if we go through the literature, they have been described as having these catabolic these catabolic capabilities. They have some enzymes that's able to degrade bone. So some papers are focusing on this catabolic activity and looking at them in that context. But at the same time, they have an osteoblastic signature. So they also have this bone-forming signature. And
where do they come from then? Maybe you don't know this. Are they are they? Where do they come from? Let's say, are they always there? Do they come from osteocytes? Are they hidden away somewhere? Where are they?
It's a good question whether they come from the osteocytes, whether the osteocytes are actually, since the osteocytes are usually considered like the final differentiation,
they're sort of
like
old,
the end of the road.
They're osteoblasts that have gone out to retirement homes, the osteocytes.
Exactly.
So possibly they could renew themselves
Possibly
as
they can
young
go back.
reversal cells. Goodness, that is exciting, because that completely turns on its head our whole understanding of how bone turnover works, doesn't it?
Exactly. But most of them are probably coming from the blood as mesenchymal lineage cells.
Mesenchymal stem cells are coming from the blood, and so they're just arriving new on the building site.
We actually do have, like, even in this compact part of our bones, we do have a lot of blood vessels coming in, and we also see, if we look like at that section, we see that when we have the active bone remodeling, we can always find a blood vessel. So most of them will come from the vasculature, from the blood, and like kind of serve as a population of new cells. But whether the osteocytes can come back and become osteoblastic or reversal cells is one of the things that's used to study in this.
Wouldn't that be amazing if they were sort of born again as reversal cells? And but it completely changed our thinking about things.
Yeah, because I don't think we know that when you remove this bone and then suddenly you meet an osteocyte, I don't think we really know what's happening to this osteocyte. But probably they play an important role in actually signaling that it's sitting in old bone, that, hey, this is bad bone. Can you please come and remove me?
There needs to be some. It's like if there's damaged piece of road, an inspector needs to say that piece of road's damaged, and we'll get then the workmen to come and dig a hole in the road and get other ones to. But you need that signal that the road's damaged, and you need an inspector to come and look at it. So maybe this is what the reversal cells are involved in some way.
Maybe I think I would rather say probably the osteocytes are like the ones telling, hey, we got a problem here, come fix me. They have like a lot of what's it called? They have a lot of extensions, so they will like actually stretch
dendritic processes and things.
Just as you see in the brain cells, they have a lot of processes.
And they connect with each other, but then they may convert themselves into reversal cells and go and start the job.
They may be, or they may just be like adding some signals that would recruit the reversal cells. So it's kind of important, and we've always, or earlier we believed that bone was such a dead tissue, nothing happens in the bone, but... Yeah,
I start off a lot of consultations with patients by saying, you probably think your bone's dead, and then you've got to convince people that it's alive. And we were talking to someone earlier, Richie, about some of the films that you see, the films where they're obviously sped up, but you can see the osteoclast moving across the surface of the bone and resorbing a pit and moving on. And I think if I could show my patients that, they would see how alive the bone tissue is and how important it is to take your medication, keep taking it, because your tissues are alive,
and remember to tell them that they are not the bad guys, these osteoblasts.
No, absolutely, they're not exactly, they're just...
They are important, we need them, but most often we've also been considering that osteoporosis is when the bone resorption becomes too much, but actually it appears like it's rather the bone formation that becomes too slow. And maybe the reversal cells are actually important in recruiting, or maybe it's just the replenishment of new bone cells that's bad when we become older.
And potentially a therapeutic target at some stage, I imagine.
Yeah. We hope that we can find some signaling that these reversal cells are like when they're calling their friends and saying, hey, it's now, come and build the new bone.
Another classic case of basic science leading to the identification of physiological pathways that could be used as a treatment target. Xenia, you're an early career researcher, and yet you are already rewriting the textbooks. How does that feel?
I think it's kind of nice to see, see how things change. Like now you just talked about these osteoclasts that move across the bone surface. I was told that the osteoclasts are just sitting there, resorbing and then moving. And then all of these studies have been done, and now it's actually been accepted that, okay, maybe they do move well. So it's a change, it's a paradigm that's shifting, and the same with these reversal cells. It's also a paradigm, and it's so nice to be like in the middle of this, and also experienced going to my first meetings that people were a bit like, really? Are you sure? And I'm just like, not completely, but we kind of have a better and better gut feeling about it.
I feel it's, potentially one of the most important discoveries in bone research for a very long time, since the recent discoveries about osteoclasts fusing together and forming new cells. And when I got back from Denmark, I had a meeting with David, and he told me he was going to go and give a lecture and he's going to talk about bone remodeling. And I was like, yeah, you're going to have to change it.
That's true, because I gave a lecture in Oxford earlier this month, and I included the reversal cell in my diagram, but I hope no one would ask me about it, because I didn't really know that much about it, and no one did ask me about it. So now I'm going to be an expert.
Now you know.
Now I know. So that's that's great.
The really lovely thing about doing this podcast is we get to sit down with the people who've made the discoveries and hear straight from them how they did it and ask our own questions, and I really love it.
Yeah, it's great. In the science world, discovering a new cell is like discovering a new species in the sort of the bigger world. So it's really exciting.
Yeah.
I think it's also a question about like discovering, because it's always been there. We just really didn't know what it was. We believed it was this kind, then we believed it was this kind. Maybe it's just an intermediate step on the way towards bone formation.
And it was the spatial transcriptomics technique that allowed you, or that was a big step towards finding this, wasn't it?
Actually, we've seen it before, so we just wanted to use the technique to look into this, because we haven't really found a marker that would be able to show us this is the cell. So kind of like saying this is actually the one we're looking for. So we just want to see what else does it do. And we can actually see from the spatial transcriptomics that it has both these anabolic and catabolic functions.
Yeah, you can see it in its natural environment where it actually is doing its job.
Yes, we can see that it has. It's making those genes, or activating those genes. That's actually important for these functions.
It's a really good example of very new technologies in the right hands being very disruptive and completely rewriting some of our understanding. We should
disruptive in a good way. Disrupting knowledge which was incomplete and replacing it with new knowledge.
The look on your face now is a look that I had when I first heard about this as well. It's amazing, isn't it?
Great.
It's absolutely wonderful. Thank you so much for coming and telling us about your work. It's really staggering.
Thank you for inviting me. It's been a pleasure.
It's a pleasure, and thank you. Isn't it great? We're also enthusiastic about bones, even though most of the rest of the conference have gone home now. Everyone's tired. We're still talking about bones with enthusiasm. So,
I don't get to tell like friends or family the same amount of details.
Yeah, you're among friends now. We all love hearing about bones.
Exactly, it's amazing.
Thank you very much indeed. It's been great speaking to you.
Thank you.
Thank you. Listeners, we're really excited to interview our last guest for BoneUP Live 3 2025. It's a friend of the podcast, Kassim Javaid. How are you doing?
Oh, I'm very well. I'm actually honoured. I didn't realise I was the last one. I don't know if that's a sign of respect or desperation, but we can fill. Am I a filler or am I the cream on the top? I'm not quite sure.
As I think I said last time, if we were a popular television quiz, you'd be one of the team captains.
Can I be Paul Merton? Ian Hislop's a bit controversial.
I think we normally talk to you about your highlights in the conference and get some perspective for you. So I think it's good to put you at the end of the episode, because we're kind of like looking back at what's happened. What were your highlights of the conference this year?
Well, you asked me about this, so I actually took some notes, so I didn't forget anything. So I think that what's really surprised me is the breadth of science, and it's really shifted. We've got everything from the zebrafish with jaw ache, which doesn't influence how much it eats, to real population and public health messaging in low and middle income countries. And I've been really happy to see the real multinational contributions, not from the usual, Australia and other countries, but from China, from India, from Africa, and really seeing the ECTS as becoming a global space that's very friendly, encouraging, and hopefully building the capacity in these countries, where I think there was an amazing figure from Celia where she compared population size and then amount of research done. And you could just see we need to develop a whole army of researchers in these countries, and any way we can help coming to the ECT and inspiring them or helping them through ECTS would be brilliant.
Yeah, that's wonderful. I've been impressed by the generally high standard of talks and science at this conference. I think that's really blown me away is the quality of the slides.
Yeah.
The images, the diagrams on slides are absolutely beautiful these days.
I think that's from the era we've got. I've seen a few AI generated images. I can just check, can you draw me an image of a kidney and a bone talking to each other? But I do agree, I think it's become much more visual and less text heavy. And people are preparing slides to communicate rather than just show data. I
Yeah,
think
well,
that's a big
it's a
difference.
good thing, isn't it? You know, the last thing you want is someone to just put up a slide with a lot of text and then just read the text out. I think people are becoming better at communicating, and you know that comes through. That's not just a science thing. Obviously, as practicing clinicians, communicating with the patient is something we talk about again and again and again. And we don't use images much to communicate with patients. Maybe we should.
Well, we once did the Draw Your Bone project.
Yeah.
So we got them to draw your bone, and we got them to draw a healthy bone, and then we got a patient to draw a bad bone, and then draw a line between them and put a cross where they were. And we just basically said, oh, no, they always underestimated how bad their bones were. We said, well, your bones are really bad. And we drew the cross, and then it was like, what should we do about it? But yeah, that's a really good idea.
The first time I ever met you was at the ROS conference where you were on stage doing that and you got us all in the audience
with
to draw a
Vivian,
bone.
yes,
Yeah.
that was many years ago. Yeah.
Yeah,
Isn't it amazing how long we've been doing this, and we're still finding out new things about osteoblasts and osteoclasts?
It's amazing, and I think also the additional sort of the breadth of bone. So I mean, we had a section on something called CRMO, a very rare autoinflammatory disease. We had a section on mastocytosis, a sort of very, very unusual cause of osteoporosis, with lots of kidney bone disease. You know, and it's a massive problem. We had a section on osteogenesis imperfecta, a rare bone disease. We had myeloma. We had other rare bone disease. We had that not new, but sort of update on the anti-FSH story.
Yeah,
Would that be a new
yeah,
treatment?
that was.
The sympathetic system as well. And then also the youngsters presenting their small bits of research.
Yeah.
Not necessarily the blockbusters, but the small steps is also very inspiring.
Yeah, and if you were here right at sort of 8 a.m. on the first day, you got to hear about the bone marrow adiposity and the really interesting story about that as well.
Pleased you picked up on Monet Zaid. We interviewed him yesterday about the FSH and the FSH blocking antibody. It's a really fascinating interview. I hope you enjoyed it, listeners. Cass, as always, one of the busiest humans on the planet. And we saw your talk just now on improving FLS with AI. And I thought it was really interesting because we've seen a lot of people at recent conferences talking about how they're using AI to try and improve frax prediction. And I sort of feel, is that kind of reinventing the wheel? Are there some bigger things we could be doing with it? And I think your project does exactly that.
Oh, thank you, Rich. That's really kind of you. So basically the premise of the project is that actually we should find all the people who've already had fractures, who've had a CT scan for another reason, and are just sitting in our hospital systems. And it really came from an observation that we had hip fracture patients, and when we went to look at them, we always look at their previous imaging, and a lot of them had already had a CT scan. And of those CT scans, a lot of them had vertebral fractures, and we denied. We've tried everything, radiology reporting, getting a nurse to look at the CT scans, and then over the last, it must be 8 years now, we've built a sort of AI program, and then we were very fortunate to be funded by the NIHR to do an important grant, which is just finished, and we sort of tested it in the real world. So not in a lab where you've got the person who invented how to score vertebral fractures reading all the scans, but just give it to a normal hospital, normal FLS, and just see what happens. And what we found, it works. It does create challenges for an FLS, and it raises the question, like you said, go back to the basics. What's an FLS for? Prevent the most fractures. And the way to prevent the most fractures, you find the people at highest fracture risk. And we've known from the beginning, vertebral fractures are where it's at. So the AI gives you a sort of very low intensity work to find thousands of patients with vertebral fractures. And we've shown they live long enough, they have low bone density, and the transformation now is to move FLSs to be AI enabled, so we can really find them.
The thing I liked about your story there was the beginning, how you had the patients with hip fractures and you were looking at their other images and seeing what you could find. that kind of just thinking about what you're doing while you're doing it and taking your time over it, leading you to that little discovery that then got you thinking about, well, hang on a minute, I love that. Just being switched on and thinking and applying critical thinking as a doctor in your daily practice really leads to great improvement of care.
It does, and I think that's a big challenge we have, because at the moment the healthcare system is all towards productivity, and if we're pushed too hard, our curiosity will suffer.
Yeah.
So I tell the juniors, stay curious. If something doesn't fit, usually it's nothing, but you need to show me it's nothing.
You know, we're so interested in vertebral fractures because from the data we've had in the past, we know they're a very strong predictor of further fracture, a very strong predictor of osteoporosis. If there are vertebral fractures just being picked up by AI, do we know for certain that those fractures would be associated with the same bad outcome as the ones that people have turned up with back pain and had an X-ray of the lumbar spine?
We don't know for sure. There is some good work from Denmark that's looked at that very question, and they looked at AI-detected fractures, other inpatients, and then the risk of another fracture. And there it was a bit confusing. Just being in hospital makes you more likely to have another fracture because you're ill.
Yeah.
And they couldn't really tell the difference. We've done it slightly differently. We've looked at the ones with a fracture, then we've done a bone density, find the ones who are low bone density, then treated them. I'm pretty confident on like basic principles that they will be at high risk of fracture because they've got a vertebral fracture, they've got low bone density. The big question was, were there other risks of disease so bad that they wouldn't survive long enough? But we know about 68% survive at least 2 years.
Yeah, you mean if you're having the CT because you've got lung mets or renal failure or something, then
it's actually the pulmonary embolus, the CTPAs are really,
yeah.
if you're a man and you have a CTPA in a hospital, that wasn't a good thing. But what we also found, it mattered which hospital you were in. And don't understand this, having CTPA increased mortality in some hospitals but not other hospitals if you're a man. And that means that we can't have one rule for all of them.
Yeah.
It's either you have no rule and just accept it, or you try and do hospital-specific things. But it's such a quick thing that AI can pick it up really quickly, and it took our nurse about 30 seconds to check a scan. So it's a very fast way to find vertebral fractures.
Yeah, it was an interesting presentation, certainly, and
Thank
well
you.
received, I think.
Where will you go next with that work? Is there going to be any possibility to expand it to other hospitals?
Yeah, so we are writing the papers. So we have a paper on what happens when you audit it, how do you implement it. We've done one on information governance, then we've done the health and cost effectiveness. We'll then create a business pack that hospitals can look at to see if I have this many CT scans, this many CT scan patients, this is the expected number of fractures I find, this is the impact on the service, and this is the impact on the patients and saved outcomes. And Richie, because they're vertebral fractures, you don't have to treat that many to start preventing hip fractures. If you have to pick one fracture that predicts hip fracture and survives long enough, it's a spine fracture. So the health economic model is actually really positive. So we will create a pack for FLSs to enhance their services, and hopefully that pack will then help the FLSs just to become more efficient at finding high fracturous patients. But no, my journey only finishes when every hospital has at least looked at whether they need AI. And then we'll also create the packages, so putting AI in is not a challenge. It's just a stepwise process of ABC. We had to create the ABC, and hopefully we can make that a lot easier.
Amazing. We'll watch with keen interest to see how you get on, and I hope that we get an update next year.
Definitely.
Thank you for joining us. It's always a pleasure.
Not at all. Thanks a lot, guys. Keep up the good work.
And see you again soon. Thanks.
Well, listeners, David and I are sitting in the airport waiting for our plane home. It's been a really busy 4 days. I'm feeling quite tired now, but it was definitely worth it.
Yeah, we learned a lot about bone. I think we come to these conferences and you always go home having learned things, but also with lots of questions, lots of ideas as well, which is really encouraging. And again, a really good mixture of clinical talks where we, as a doctor, you learn from other doctors about how better to treat patients, lots of interesting science and new research, and then lots of opportunities for scientists and clinicians to sort of meet together and talk about how we work better together.
Yeah, it was fascinating this year. We learned a lot. I felt the talks were very broad and encompassing of the bone field. The plenary talks, invited speakers gave really excellent talks. I think my personal favourite was the talk about the relationship between chronic kidney disease and osteoporosis, explaining the relationship between the pituitary gland, PTH, and bone resorption, and all of the other impacts that it has on the rest of the body. What was your favourite talk?
Yeah, I mean, there's a number of things stood out. I think right at the very start, there were some very interesting presentations on bone marrow adiposity and the observation that increasing bone marrow adiposity, in other words, more fat cells in your bone marrow, that's not good for your bone. That's associated with osteoporosis. But interestingly, both as overall body fat goes up, adiposity in the bone marrow goes up, but in patients with anorexia or patients who have lost weight dramatically, even though they lose fat elsewhere, adiposity in the bone marrow remains, or in fact goes up as well in those circumstances. So there's something very interesting going on there. And that has potential implications, and of course implications potentially for developing drugs as well. I think the other thing that stood out for me was the presentation, and I know we actually spoke to him, and you will have heard him talking to us folks, Monet Azadi, about his work on FSH. And I think as a clinician, that's one of those things. Over many years, you measure estrogen levels, you measure FSH, but really it was only the estrogen levels we looked at and associated with changes in bone. The fact that actually FSH may itself be associated with changes in bone and could potentially be a target for treatment and new drugs, and a very direct and obvious target for new drugs and treatment, well, that's quite exciting, and it remains to be seen just what comes from that research.
Especially in the very early stages of bone loss. It feels like it could be a very preventative medication.
Yeah.
I agree. I thought the talks around adiposity were really interesting as well. And one thing I think is that really the science seems to have leapt forward in the last year. At last year's ECTS, I remember we spoke about adiposity, we spoke to Jeroen Geertz, and we learned about, the distribution of adiposity in bone, etc. It feels like in the last year, that field has really moved forward quite a lot. And now, just 12 months, people are understanding a lot more about how changes in overall body mass and weight relate to changes in adiposity in the tissue, and how changes in adiposity in the tissue in the bones might affect osteoporosis.
There was always that interesting observation, in patients, that if you saw someone who was very, very light and very frail and had very low body weight, low BMI, well, that was associated with osteoporosis and with bone weakness. But the converse wasn't necessarily true. People who were very obese and very overweight, we've known for years that actually that can drive osteoporosis as well. So there's that interesting sort of dichotomy, and it may all be related to bone marrow adiposity. So lots more to find out there. And I mean, in the sort of the clinical world particularly, we were talking, or there were presentations looking at denosumab, looking at teriparatide, the PTH analog, some mention of abaloparatide as well, the new TTH analog or PTH-related protein analog, and then romosozumab as well. And while I think in the last few years people have been thinking in terms of comparing those different drugs to work out sort of which is better, to put it very simply like that, I think people are slowly moving towards the idea that it's actually the sequencing we should be thinking about, because actually all those drugs work well under certain circumstances for certain patients. And the question we should be asking is, which do I use first in my patient? How long do I use it for? Which drug do I switch it to? Do I switch the patient to? Which drug do I use next? We were starting to see some discussion of that, actually, sequencing as opposed to just sort of head-to-head work. And again, I think the emergence very much of the concept that we have anti-resorptives, which are bisphosphonates, and denosumab, which reduce bone loss, that we have osteoanabolic drugs, teriparatide and abaloparatide. And actually, while romosozumab is generally lumped in with the osteoanabolic drugs, in many ways it's a third different type of, because it acts on a different pathway, the WNT pathway. It promotes bone growth and reduces bone loss at the same time. And I think as other work is done on that pathway, the WNT pathway, there's potential for new drugs to come out targeting that pathway. I think it will eventually be considered that there are 3 pathways rather than just 2.
I agree. I feel that maybe romosozumab is better described as a bone-forming medicine as opposed to an anabolic medicine.
Yeah, it is. It's different from the other osteoanabolics which activate PTH receptor. It obviously acts in a different pathway, and therefore perhaps we should sort of categorize it differently.
One thing that stood out for me that's quite exciting is a possible of combination drugs. In previous conferences in the last few years, drug sequencing has been a big topic, and now, as you mentioned, all these drugs, they're available. You as a doctor have got an opportunity potentially to use them in different sequences for different amounts of time to get the best outcomes for your patients. This conference was the first time I'd seen drugs used in combination at the same time. And if you do have 2 or 3 different types of drugs that act on different pathways, then maybe by putting them in combination you can get better outcomes. It reminds me of taking paracetamol and ibuprofen at the same time to get double the pain killing.
Yeah, that's something people have looked at a bit in years, over the last few years, and it would seem obvious maybe to give an osteoanabolic drug and an anti-resorptive at the same time. Looking at experience across many other diseases apart from bone disease, as you combine drugs to get greater efficacy, you also run greater risk of side effects, of course. That's always the problem, I think, with combining drugs. But certainly it's something we'll be looking at a lot more. And yeah, again, another interesting area of study. And of course, we heard about a new cell as well. It's not often that we hear about a brand new cell in sort of basic biology. So what did you make of that, the reversal cell?
I thought that was quite incredible. I thought it's a very good example of how a technological leap forward allowed scientists to answer questions that had remained unanswered for a really long time. And the development of spatial transcriptomics and the ability to conduct that in laboratories which are associated with hospitals meant that for the first time we could get human tissues into the systems in large numbers for long periods of time, and it allowed the scientists, southern Denmark, to really look at that very intricate process that takes place between osteocytes resorbing bone and osteoblasts putting new bone back. I think for a long time we hadn't really known what was going on there, but because there wasn't really any way of looking at it, we kind of just sort of ignored it, really. But as soon as the technology became available, people got straight on it to go back and solve that really interesting problem. I wonder how much more we're going to hear about bone reversal cells in the next few years as people start to think about what role they might have in the etiology of osteoporosis, pathophysiology of the disease, and whether or not there are some people whose osteoporosis might be treated by targeting the sequence of events around a bone reversal cell. That's really exciting.
Yeah, and you heard it here first, folks.
So I suppose we're going to have to go and get ready for our flight now. But we should thank a few people before we go. We'd like to give a big thank you to the whole ECTS Society who supported us, not just this year, but in previous years at the conference. The past president, Bo Abrahamson, the current president, Peter Peachman. We should also give a shout out to the ECTS Academy. They've been going for 10 years now. They've been incredibly supportive. Jeroen Gertz, who helped us get going earlier, and a really, really big shout out to Gonzalo Diffuse. Gonzalo, if you're listening, thank you so much for all the help you've given us over the last few years, finding us good guests. And we should also thank the IFMRS as well. They've been able to get some really good guests for us. And I really enjoyed their session on the digital twin. Thank you, everyone.
And thank you to our colleagues at work and indeed our families at home who allow us time to come to these conferences as well. We've got to put that in, Richie.
And thank you, listeners, for joining us. We hope you had fun listening to the podcast and that you learned just as much as we did.
And we'll see you soon back at one of our conventional episodes. Bye now.